Okay, so I'm going to get started because we're tight on time. I still have to do 3 sections in 10 as well. I might be able to do 1 section of 10 along with this one today. So let me just get started. And I will make the recording available later today. So the last thing we talked about last time, guys, is studying the relationship between 2 variables, x and y. And I did show you an example. For example, if you have those ordered pairs, x and y values, if we plot them using the calculator, we will get something like that. You notice, guys, that as the x value increases here, the y values increases. So we're tempted to say that there seems to be a relationship between x and y. And the relationship is the following, guys. As x increases, the value of y increases as well. This is similar to what you learned in intermediate algebra when you learned about the equations of the line y equals mx plus b. This is exactly what we're doing here. Now, we said last time that the relationship is not perfect because not all the points would fit on one line. But there is a line that I can draw right here, guys. And this line here is called the line of best fit. This is the closest, this is the line where most of the points are very close to it, and it is called the line of best fit. Because there is a line where all the points can come very close to it, then we say the relationship is linear relationship. Now, how strong, guys, the linear relationship is depends on the value of R, which I told you, they talked about it last time. R is called the sample correlation coefficient. It is a value that we will use the calculator to find. And if R is very close to 1, we say that there seems to be a strong positive linear relationship between X and Y. If R is very close to -1, we say there seems to be a strong negative relationship between X and Y. And if R is close to 0, we say that the relationship is weak. And R is called sample correlation coefficient. You don't need to find R by hand. I will show you again how to find R using the calculator. And all the details about how to make a conclusion about the value of R are given in this handout. Again, if R is very close to 1, we say correlation, that there seems to be positive strong correlation between X and Y. R close to -1, negative strong correlation between X and Y, and R close to 0. What is close to 0? Like, for example, 0.10, 20, 30. But when you go to 0.80, 0.85, 0.95, this is very close to 1, then you say there is strong positive relationship between X and Y. X, guys, as you know from intermediate algebra, it's called the independent variable, and here it is called the explanatory variable. And Y is called the dependent variable, and it's called the response variable. So response is the dependent variable, and explanatory is the X variable, independent variable. For example, guys, the number of hours you work and income, the wages that you make. You know your wages depend on the number of hours you work. So your wages are the dependent variable, are the response variable, and your hours are the independent variable. So this is how we can tell which is which. Okay. So this is something I touched on last time. This is the line of best fit that I told you about, guys, which we will go over one more time, and the calculator can find the equation of this line. They call it the line of best fit. You will be asking the homework to find this equation of the line, or they call it the regression line, or it has a name, equation of least squares line. So all three lead to the same thing. And again, as you can see my note, guys, you will use your TI calculator to find the equation of the line of best fit. And the equation of the line written like this, guys. If you remember that from intermediate algebra, M is called the slope of the line, and B is called the y-intercept. The y-intercept is where the line crosses the y-axis. So for example, if I do this, this is the y-intercept right here. And the slope is rise over run, the steepness of the line. This line has a positive slope because as we move to the right, this line is going up. But if you have a line that goes this way, then they will have a negative slope because as you move to the right, the line is pointed down. All right, again, this is what I reviewed, I talked about last time. If R is very close to 1, we say there is strong positive linear correlation between X and Y. I put all the details in this handout, guys. I didn't miss anything. If R is very close to 1, we say there is strong negative linear correlation between X and Y. And if all the points are on the line, then R is perfect, either 1 or -1. So if you have something like this, guys, if you put all the points, you can connect them all in one line here, R equals 1. You want an example where R is -1, it will be something like this. This is R equals -1. Let me see if I have any questions here. Okay, no questions. Okay, so this is our, these are optimal situations, guys, where all the points fit on the line, all the points fit on the line. If it misses one point, guys, then R cannot be -1 here. Now, how do you find R, or how do you find R on your calculator? I asked you last time, guys, and you make sure, for the sake of chapter 9, you do this. You press the second key, and then you go down to number 0. Then you're gonna get this, and you make sure that your diagnostic is on. And if you reset your calculator for whatever reason, you have to do this again. See, done, diagnostic on, enter, enter. It is on. Then your calculator is programmed to show the value of R in a little bit. So this is how you make sure that R will show. We'll talk about it in a minute. Okay. Now to do a scatter plot, how do you draw a scatter plot? I'm gonna go over this one more time today. So what we're gonna do, guys, I'm gonna explain all of it, chapter 9, through this example that I'm gonna do right now. So example 1, this example covers all the objectives of chapter 9 that you need to know. So I will pause the recording for 1 minute until you guys go to L1 and L2 and input the X values in L1 and the Y values in L2. So please do that with me. Yes. So here's what I like you to do now. To make sure, if you were not there last time, so this is what we're gonna do. Now, in order to show the scatter plot, you need to press the second key and Y equals. All the details are in the handouts as well. Plot on. So second and Y equals, enter, and then make sure that on is selected right here. Type is the first one. Press enter. And make sure if you put your data in L1 and L2, make sure it says L1 and L2 right here. If it doesn't, and you have your data in L1 and L2, it's not gonna work. How do you change L1, for example, to L3? You just press the second and then number 3. Well, actually for me, guys, I put him in L3 and L4. So I'm just gonna change this one to L3 and L4. But leave it as L1 and L2, guys, if you put him in L1 and L2. So And I'm gonna quit. Here's how you quit the screen, guys. You just press second and quit. All right, and let's go to the question. Now, the real question that covers everything in chapter 9. Let X be the age of a child in years, and let Y be the number of irrelevant responses on a standardized test appropriate for the child age. So we have a data set that gives us the child age and how many questions will have irrelevant responses depending on this child's age. I mean, for 2 years old, you don't expect them to think critically, and you know, when they respond to questions, they're not going to think critically, so they're going to have a lot of irrelevant responses. So it looks like there is a relationship between the age of a child and number of irrelevant responses. You notice, guys, here, as they grow older, the number of irrelevant responses tend to go down. And that's, I think, I tend to believe this because they start thinking, you know, just logically and critically, you know, just as they grow older. So this is what the table is about. The first question is to create a scatter plot of the data. Here is how you do it. You go to Zoom. You already set up stat plot and it is on. You just press Zoom and then number 9, guys. Oops, let me delete this. That shouldn't be there yet. Okay, so Zoom and then 9. There you go. That's what I got right here. So do you guys agree with me? There seems to be a relationship between the age of a child and number of irrelevant responses, but it's not a positive relationship. It's a negative relationship because, as you see, as the X values increase, the number of irrelevant responses decrease. So it is a relationship, but it's a negative relationship. So the next question is to find the correlation coefficient R and explain it. So we need R. Okay. You see, find the correlation and comment on the relationship. Here is how you find R, guys. You press stat. You don't need to take notes. It's all in the handouts. Sorry. Stat. Calc. Oops. Stat. And then calc. And it's number 4. Linear regression AX plus B. Now, this is by default, guys. They will do L1 and L2, but I did my data in L3 and L4. So look how I tell the calculator to go to L3 and L4. I press the second key and then number 3, comma, and then I'll tell the calculator to use L4 as well. Now, if you put your data in L1, L2, guys, there is nothing you need to do. Just, you don't need to do L3, L4. But I meant to change, you know, the list so that you know how to work with different lists as well. Okay. You can see the value of R is negative 0.971 if we do 3 decimal places. It's right here, guys. And not only it will give you the value of R, it will give you the equation of the line as well, which we will need later. So let me take the value of R right now, negative 0.97. You can see lots of details in my handout because I'm explaining how to do everything. So using the calculator by following the steps above, R is negative 0.97. Since R is very close to negative 1, we say there is strong negative linear relationship between X and Y. X is the age and Y is the number of irrelevant responses. Any questions, guys? And how to comment on the relationship? When you do your homework online, you just, there's a drop-down menu. You select, you know, like there could be one answer. It says a strong positive linear relationship. Definitely you don't want to select that. You want to select the strong negative relationship because R is negative. If R is negative, guys, the slope is negative as well. And if R is positive, the slope is positive. Part C. Find the equation of the line of best fit regression line. Use your calculator and the steps explained above to derive the equation. Well, you already have the equation, guys, right here. So let me just write it down. A is -0. I'm going to do 3 decimal places. X plus 17.296. This is the equation of the regression line. Now, they call it in the book Y with the hat, just to say that this was derived from a sample. And let me show you the line of best fit, guys. Let's sketch it. So click here, Y equals, enter it. For negative sign, please do not use this sign right here. Use this one, negative. 0.963, and here is X right here. X plus 17.296. And click on graph right here. And watch, guys. See magic now, the line of best fit. This is the line of best fit. You notice all the points are very close to this line. So this is what we call the line of best fit. It's very, very difficult to do this by hand and find the equation of this line. But technology will go through all the options until I find the best line that fits the points, and then I will give you that equation. Okay, guys? So we did a scattergram, a scatter plot. We found R. We learned how to comment on the value of R. And then we found the equation of the line, which is called the equation of the regression line, or the line of best fit. The next part is the most important part. It's part D. So let me explain D before I get into it. This is where I need your attention. This is the heart of this chapter. Okay. We notice that R is negative, and we notice that there seems to be a relationship between the age of the child and the number of irrelevant responses. And R that we got, which was negative 0.97, we got it, just based on the information from the sample. And this was the sample right here, guys. Right here. The question is, this is the big question. Based on the information in the sample, we say that there is a relationship between the age of the child and the number of irrelevant responses. The big question is, can you extend, just this saying and say that there is a relationship between any child and the number of irrelevant responses? That means, can you extend, just our findings to the entire population of children? So can you extend, this to the population? Just like what we did in chapter 7. We tested the mean, we tested the proportion, we tested the difference between two means. And now R tells us that there is a negative relationship, but can you say in general that there is a negative relationship always? Well, in order to answer this question, guys, we need to do a hypothesis test. The value of R that I found, it's called the sample correlation coefficient. It was from the sample, as you noticed. Now what we need to test this. And this is called rho. This is pronounced it rho. Let me tell you what rho is. It's the population correlation coefficient. I can never find the population correlation coefficient, guys, because in order for me to find the population correlation coefficient, I have to have all the children in the world take the standardized test and record their irrelevant responses, which it's impossible to do. But I can use the value of R to make conclusion about the value of the population correlation coefficient, just like what we did before. We used X bar to make a conclusion about the mean, or we used P hat to make conclusion about P. Now we're going to use the value of R to make conclusion about the population correlation coefficient. It's called rho. This you can never find, guys, but you can test the claims about it. So I'll go back and I'll show you how we're going to test rho. So rho is, again, a population correlation coefficient. There will be 3 scenarios, guys, that you can test. In this question, he says test for negative correlation. So I'm going to show you how to list this one. Negative correlation means you need to test that rho is less than 0. And then the other hypothesis, guys, will be greater than or equal to 0. If he asks you test for positive correlation, look what you do. I know this is the hard part, guys. Just bear with me until I'm done with this. Rho is greater than 0, less than 0. But if he asks you to test for correlation, he doesn't say positive or negative. Look what you write. Okay. Less than 0 means you are away from 0 to the left. That means you're not close to 0. And remember, when we are close to 1 and -1, correlation is significant. We have correlation. So when you are less than 0, that means you are away from 0. You write here, correlation is significant. So always in the alternative hypothesis, correlation is significant. Here, greater than or equal to 0. Equal to 0, when R is close to 0, we say correlation is not good. So here we write correlation is not significant. So there is no claim or no claim here or there. You just write those 2 statements. Same thing here. Correlation not significant. Correlation is significant. Significant means it's strong enough to talk about it. I'll give you an example of significance. Like a student had a 70% score on test 1, and then on test 2, he got 72%. Is this a significant improvement? No, it's only 2%. But if a student got 70% on test 1 and then 95% on test 2, the difference 25, the improvement is significant in this case. And here, equal to 0 means no correlation, correlation not significant. I'm not saying, guys, you have to use all 3 of them. It's just one of them always. And here, correlation is significant. Okay. Since he asked me to test for negative correlation, guys, right there, then that's my statement. This is going to be it. Less than 0. So this is the outcome that we're going to be using right here. Okay. And let me show you how to run the test. It is called the t-test, a linear regression t-test. And I'll take it to the calculator. You already have the data into your calculator. You don't have to do anything. You just run the test. On stat, tests. Okay, scroll up, guys. So I'll wait until you do this and scroll up. And can you guys see the test that I'm talking about? Even if you get confused here and say, which test do I want to use? Remember the title of that chapter. It's Regression and Correlation. So it is a linear regression t-test right here. Okay. If you put your data in L1 and L2, leave it. But for me, I put him in L3 and L4. So I'm going to change this one, guys. Don't change this number, the frequency. It's always at 1. Okay, here we need the alternative hypothesis sign. What is the alternative hypothesis sign here, guys? It's right here. Less than. Just like what you did in chapter 7 and 8, you choose the alternative sign. And I'm ready to hit calculate. Okay. This is the test statistic, negative 10.74. Let me write it down. P-value. This is the p-value, guys. You can see it's 6.656 e negative 6. Let me write it down here. Which means you have to move this 6 decimal places. So it will be 0.000000656, which is almost 0, guys. So you can write 0, which is less than alpha. And if the p-value is less than alpha, what do? You reject HO. Okay. If you reject HO, there's what you say, guys. You say there is, I'm gonna write it down. It's written, but write it down one more time. There is enough evidence at the 1% level of significance to conclude. We don't need to say the word support the claim. Just put conclude that correlation is significant between age of child and number of irrelevant responses. On a standardized test. That means, guys, we conclude that what we found out about the sample works for the population. There is a strong relationship between the age of any child and the number of irrelevant responses. Can a student tell me, if you can guess, if we fail to reject HO, what do we say here? There's a slight change that you have to make. What would you say if you fail to reject HO? So it's either this statement or another statement. Only 2 choices, guys. What would you say if you fail to reject HO? Let me see. Not enough evidence. Exactly. Exactly. There is not enough evidence to conclude that correlation is significant. And actually, guys, you'll be asked to choose between those 2 always. So if you reject HO, conclude that correlation is significant. If you fail to reject HO, conclude that correlation is not significant. That's it. Now, the test statistic that I found, guys, has a formula. This is the formula of the test statistics. I'm not going to require you that you do the formula, but if you did this formula, guys, you will get this value. It is R over 1 square root of 1 minus R squared n minus 2. N is the size of the sample. How many children were involved in there? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9 minus 2. And R, you already have found using the calculator. You just put the value of R. It's going to be negative 0.97. And here 1 minus square R divided by n minus 2, you will get negative 10.74. Or very close to it. It might not be exactly negative 10.74 because we round the value of R here. Okay, so this is a part D. Part E. Okay. Before I get into part E, let me just explain one more thing for you here. This part, so I'm going to repeat it, I think. So here is another shortcut, guys, to find whether correlation is significant or not significant. If you are given this table, it's called table 11. You can do a shortcut without having to go through the 5 steps of hypothesis testing in order to tell whether correlation is significant or not. In our example, R was negative 0.97. We take the absolute value of R, which is 0.97. Then our sample size was 9. We use the sample size and the alpha value that's given in the problem to find what we call the critical value, which is 0.798. The table says, if your correlation coefficient in absolute, the correlation is significant, if your absolute value of R is greater than the value of the table, which is the case, guys. Our absolute value of R is greater than we can conclude that correlation is significant. And that goes in line with my finding here, guys. As you can see, there is enough evidence to conclude that correlation is significant. Okay. Next question. Let me just take this off. All right. Part E. That should be an easy one. That's an algebra question. Find the predicted number of irrelevant answers y when the age of the child is 8. We did find the equation of the line, guys. Y hat was, what was the equation of the line? Let me write it down. It is on the calculator, so let me show you the equation of the line. So we go to stat, calc, number 4, linear regression AX plus B, and for me it's L3 and L4. For you guys it's L1 and L2. Okay, let me write the equation of the line. Y hat equals, so we use a hat just to say this is from a sample, with 3 decimal places 0.963x plus 17.296. All right. That could be a separate question. It'll ask you to write the equation of the regression line. So this is the equation of the regression line. Or line of best fit. Can someone tell me how to do this one? He says, what would be the number of irrelevant responses if the child's age is 8 years? What would you do, guys, here to find it? That should be easy. That's algebra here, not statistics. Yeah, plug 8 into X. I agree with you. Just so Y hat will be negative 0.963 times 8 plus 17.296. And it is about 9.59. I already did the work, guys. Yeah, which is almost 10 answers. Or 10 responses. You have to round it because you can't have a partial response, so it's 10. This is how we do that. But let me share this with you before I go to the last part, which is part F. If I ask you to find the number of irrelevant responses, y when x is 15. Let me take you back to the table and show you that we cannot use the equation to find y. Can you guys tell me why? Let's see if you can tell me why. I wouldn't ask you to find the number of irrelevant responses if the age of the child is 15. I was okay with 8, but not with 15. Can you tell me why, guys? Look at the table. Any guesses? Why it wouldn't be possible to find the number of irrelevant responses if x equals 15? That means I could not plug in x equals 15 into the equation. Why is that? Why am I saying that? Any observations, guys? Look at the table carefully and tell me. Does anyone know why it wouldn't be realistic to do that? Let me see. I got a few responses here. No, there could be 9 or 10 values. That's not the not because there's only 9. I could ask you to find the number of irrelevant responses if x was 4.5. No problem. That would work, but it wouldn't work for 15. Okay, let me tell you why. You notice the smallest age of a child that you have in the table, guys, is 2, and the largest is 12. So any questions that has to go beyond between 2 and 12, anything beyond that, the model might be a breakdown and would not be able to be probably it's not appropriate to use the model beyond the 12. So that's why, because X is 15 equal 15 is more than the largest value in the table, we will not be able to use that. In the homework online, you would just say it's not meaningful to find the value of Y using X equals 15. And he'll give you the option to say not meaningful. But if I insist on you guys, and I told you I need the value of Y when X is 15, here is the compromise that statistician would do. You can add all of those Y values and divide by 9, which will get the average of the Y values, and use it for X equals 15. You'll use it for X equals 16. You'll use it for X equals 17. It's the same value. It's just the average. But to plug it into the equation, it's not meaningful, guys. Okay? So this is for that part. Let me go back now. Over here. And the last question that you will see, it's a part F. Find the coefficient of determination, which is called R squared. Your calculator already done R squared for you guys. There you go. It's already here. 0.943. So let me just write it down and interpret that for you and explain it. Okay, let me explain the coefficient of determination. This is very, very important concept in statistics. I want to explain it, guys, using a different example, so you will have a sense of that coefficient of determination, see how important it is. Let's say we talk about the price of diamond. Let's say I have some data that shows the weight in carats and the price. So if you have a 0.25 carat piece of diamond, probably the price is $500. I'm just making this up. 0.50 carat, it's 1,000. 1 carat, it's 1,000, 2,000. 1.5 carat, 4,000. 2 carats, 7,000, and so on and so forth. Do you guys agree with me that there is a strong positive relationship between the weight and the price of diamond first? Can we agree on that? Real diamond, I'm not talking about a cubic zircon. We should agree that there is. The more weight you put in your one piece of diamond, guys, the higher the price is going to be. It can go to millions of dollars when you have a solid piece of diamond that is 10 or 15 carats. So you're talking millions of dollars here. So let's say I found R and it turned out to be 0.87. Okay. What I like you to do, guys, so R is the correlation coefficient between the weight and the price of diamond. I would like you to do R squared for me. So 0.87 squared. Let me do this. Okay, this is what I got. .757. Okay, I like it to change it to a percent. Can you change this to a percent? So it will be 75.7%. Okay. Here's my question to you guys. Is the weight of the diamond the only factor that determines the price of a diamond? Yes or no? I'm sure I'm going to see a no here. Yes? No, there are some other factors, guys. Can you tell me about them? So other factors that determine the price of diamond. Courtney, you said no. Can you tell me some of the factors? What do you think people would look for when they shop for diamond other than the weight? Cut, very good. What else? This is why I gave this example, because students can give me some feedback here. What else other than the cut? It's important, and the price. But the weight is the most important factor, guys. Don't misunderstand me here. It is the most important factor. What do you think? The clarity, which is called the purity. The shape. And there's another factor, guys, which is very, very important. Can you think of it? Color, very good. Okay. So let me explain what R squared. Now I'm ready to tell you what R squared means in the case of diamond prices with weight. R squared, which is 75.7%, this is what it means, and this is how you interpret. You say 75% 0.7. I'm going to make it 76% to make it easier for me to make a statement. 76% of the variation in the price of diamond can be explained by the variation in weight. So the weight is not the whole story. It's not the 100% of the story. It's only 76%. The other 24%, guys, that you were able to assist me in getting them are, so 24% of the variation in the price of the diamond can be explained by other factors such that the cut, the clarity, the shape, and the color. So if you have R squared and he asks you to write it down and explain it, this is what you write. You write 76% of the variation in the Y variable, and the Y variable here is the price, and the price of diamond can be explained by the variation in weight, which is the X variable, using the regression line, because they're both related with the regression line. So this is how you interpret the coefficient of determination. This is what we call the coefficient of determination. If you're doing homework online and he says, find the coefficient of determination, guys, you know he's asking you about R squared. Okay, let me go back to my question and interpret the value of R squared. So it is 94, 0.943. Change it to a percent. Okay, remember my X variable is the age and my Y variable is irrelevant responses. So look how I put my statement. I say 94.3% of the variation in the number of irrelevant responses on the standardized test can be explained by the change or the variation in age of the child. There you go. 94%. Watch, guys, right here. It's already given, you know, you don't need to write anything. 94% of the variation, the number of irrelevant responses on the standardized test can be explained by the variation in the child's age using the regression line. Okay? So this is how we interpret the value of R squared. That's very, very important concept in statistics, to find R squared and interpret its meaning. And to go back to this, guys. One second. Okay. To go back to this, I'm going to go to stat tests. Just show you one more thing in the test. Linear regression t-test. That's what I did. Okay. Let me show you what you would get here. You get the equation. So if you run the linear regression t-test, guys, you will get the equation. If you don't want to go calc and linear regression, ax plus b. But look at the equation. It's a plus bx. So when you write the equation as your answer, make sure your a is the a that you see here, and your b is the b that you see here, and you write it not as ax plus b, a plus bx. This is the test statistic. This is the p-value. This is a. Let me show you what else, guys. This is b. And it's going to show you R next. I'll talk about S in a second. And this is R squared. And this is R. Now S. S is called the standard deviation of the observed values. So if you are asked to find the standard error of the correlation, this is S. If he asks you to find S, you have to run the test in order to find the value of the standard deviation of the observed values. It's right here. You see, it's a very complicated formula to use, guys, to find S, but you can do it nicely on the calculator. It's called the standard error of the estimate. It is the standard deviation of the observed Y values above the predicted values. Okay, the observed values, guys, are the values that you are given in the table. These are the observed values of Y. Let me tell you what the predicted values are. The predicted values are the values when you plug in X equals 3 into the equation, you get another Y value. This is called the predicted value. So this is the observed, this is the real one. And the one that you get from the equation, the Y values you get from the equation is called the predicted values. So if you are asked, guys, to find the standard error of the estimate, it is S. You will run the linear regression t-test to find it. All right. Next, we're going to do another example before we wrap this chapter up. And it's going to be, I went over all of this right here. Example 2. What I'm going to give you guys a minute to plug in the values X and Y in L1 and L2. So let me pause for a second and please participate with me. I'm assuming that you are participating. Let X represent the average amount, annual hours per person spent in traffic delays, and let Y represent the average annual gallons of fuel wasted per person in traffic delays. Do you guys agree that there is a relationship between the number of hours you get stuck in traffic and the amount of gas you waste? Do you guys think it makes sense to say that there is a relationship between the two? There is indeed. You wait more in traffic, you're gonna waste more gas. That's what, as simple as that. So I got the data. The first question, find the value of the correlation coefficient. Okay, here's how you find it. Stat, calc, number 4, enter. Okay, my correlation coefficient, guys, is 0.794. There you go. So, and not only that, I'm gonna just write the equation of the line. Let's write the equation of the line just in case if they ask us to do it. So what is it? 1.44x plus 2.81. And I'm gonna write R squared, guys, if we need it later also, 0.63. Okay? Just 1 second, guys. So we got R squared, which is 0.63. Okay. First question, R equals 0.794. If he asks you to comment on the relationship, you say there seems to be a strong positive linear correlation between the number of hours wasted in traffic and the number of gallons is used. Part B, at the 1% significance level test, the claim that rho is greater than 0. So if you state the null and the alternative hypothesis, guys, it's going to be rho greater than 0 here. Correlation is significant. And here rho is less than or equal to 0. Correlation not significant. As I stated before. Okay, we run the test right here. Stat, tests, linear regression t-test. Okay, my data is in L1 and L2 this time. So I'm going to change this one to L1 and L2. Okay, we're testing for positive correlation, guys. So we need to make this greater than 0. And then hit calculate. And here you go. T is 3.204. Let me write it down. Step number 2. Step number 3, I think you're used to it already. The p-value is 0.0093. And this is all I need from the calculator. And not only the calculator gave me this, look, it gave me the equation of the line, guys. It gave me S if you are asked to find the standard error of the estimate. It gave me R squared. You see, I already put that in there. And it gave me R. There you go. So this is less than alpha. And then you say there is enough evidence. I don't care what alpha is, even at 1%, it's very small, so it's going to be less than alpha. There is enough evidence at the 1% level of significance to conclude that correlation is significant. So this is how you test this. Now, if he asks you guys to do the test using the critical value approach, let me show you. Using the table. He didn't here. He says test that rho is greater than 0. He didn't say using critical value. So R is, what was R? 0.794. Okay. And what is N in my case? How many in traffic delays here? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And alpha is 1%. So look what you do, guys. It's very easy. 8, 1%, this is the value. Okay, what did we get here? So R was 0.794 and okay. There's going to be a conflict here. As you can see, the 0.794 is not bigger than 0.834. So if you use the critical value approach, guys, you're going to end up failing to reject the null hypothesis here. And the reason why it happens here, if you round 0.009, guys, to the nearest to 2 decimal places, what would you get? Can someone tell me what would this round to if you round it to 2 decimal places? It will be 0.01, so it will be exactly equal to alpha. And this is why, you know, the 2 tests sometimes don't agree. The reason why, because this table has, the values have been rounded. So in this way, you know, just you're going to get a conflict, you know, just between the 2 responses. But so I'm just going to stick to what I found right here, the 0.009, which is less than 0.09, and base my conclusion, you know, just on this fact. Part C, predict the number of annual gallons when X is 30 hours. You already have the equation, guys. Y hat is 1.44X plus 2.8. So if you want to figure out the number of gallons wasted, you just plug in X equals 30. So that will be Y hat equals 1.44 times 30 plus 2.81. And what do we get here? Let's do this. 1.44 times 30 plus 2.81. I got 46 gallons. Okay, the last question I want to do with you guys and find R squared and interpret its value. So what is R squared here? So I'm just going to add one part here, R squared. Well, R squared is 0.63, and let me show you how to interpret its value. So 63%, you say 63% of the variation in the Y variables of the variation in the number of gallons consumed can be explained by the variation in the number of hours. Variation in the hours spent in traffic delay. It means, guys, that the number of gallons wasted not only depend on how much time you waited in the car in traffic delay. There are some other factors. Can you guys share some other factors that could cause the car to consume more gas, not just because you're stuck in traffic? There are some other factors. Can you share them? And actually, the other factors are about 37% of the story. Can you guys tell me what other reason would you think of that would cause the car to consume more gas while waiting in traffic delay? Any ideas? You drive cars, you should know. What other factors? So waiting in traffic for some time is not the only factor that caused the car to consume more gas. It is a big factor. It's 63% of the story, but 37% of the story are other factors. Can you think of some? I'm sure you can. What other factors? Okay, AC. Using the AC, that's one factor. Okay, good. AC or the heat? Probably. Age of the car. If you have an older car, guys, it's probably will consume more gas than a newer car. Age of the car. The size of the car, is it a V4, V6, V8 engine? If you're driving a big truck, it might, just consume more gas. Mechanical issues with the car. Etc. So you can see what R square means, guys. R square, tell you what percentage of the variation can be explained by the model and what percentage of the variation cannot be explained by the model. If you see a question on the homework, it says, what percent of the variation can be explained by the model? You say it's 63%. But if we ask you what percent of the variation cannot be explained by the model, guys, you say it's 100% minus 63%, which is 27% or 37%, sorry. Okay, so that concludes chapter 9. Let me see. Okay, I still have time. I need to go through section 10.4. It's a very easy section. And just give me 1 second to prep my handout for this, and it shouldn't take much time to do this. So have your calculator handy, guys. We're going to do section 10.4, and tomorrow we'll do 10.1 and 10.2, just 2 sections. We're omitting 10.3. So we're just doing 10.4. One-way ANOVA. One-way ANOVA means one-way analysis of variance. And let me tell you what this test is going to be used for. You learned in chapter 8, guys, how to test if two means are equal, if one mean is bigger than the second, or if one mean is smaller than the second. So you learned how to compare two means. What about if I have more than 2 means? I have 3 population means, or 4 or 5. There is a test that we can check if all the means are equal, or if one of those means is not equal to the others. And this test is called one-way analysis of variance. It's called ANOVA. It is a hypothesis test technique that is used to compare the means of 3 or more population. The analysis of variance is abbreviated by ANOVA, and it is the last test, guys, on your calculator. You will see that in a second. Now, in order to run this test, some condition must be verified. But if he tell you run the test, you don't need to verify the conditions because they are assumed to work. Each sample must come from a normal population. So the samples must come from a normal population, guys. The samples must be independent of each other. So this is condition number 2. And the 3 population or the 4 population, if I'm doing 4 means, they must have the same population variances. If those 3 conditions are met, then we can perform the test. Now, the nice thing about stating the null and the alternative hypothesis of the test, it is one statement. You use it for every single problem. And this is the statement, guys. he'll either ask you to check if all the means are equal or if one of the means is at least different from the others. So when you state HO, guys, this is what you write. mu1 equals mu2 equals mu3. If there is 4, you put equals mu4. If there is 5, you put equals mu5. And here, when this statement, you put it in every single hypothesis test of the analysis of variance. So at least one mean is different from the others. So this is statement 1, and this is statement 2. How do you know where the claim is? If he says test that all population means are equal, your claim is in HO. If he says test that at least one mean is different from the others, then your statement, your claim is in HA. I'm going to take you to an example, guys, right away and show you how we run this test using the calculator. I like you to take a minute to enter those 3 data sets in L1, L2, L3, please. That would be the example, and then we'll wrap it up after this, guys. A researcher believes that the mean earning of top paid actors, athletes, and musicians are the same. So he believes that all get paid the same. He collected data for how much, just actors get paid, how much athletes get paid, and how much musicians get paid. They're earning in millions of dollars. Oh, wow, I thought thousands of dollars. It's millions of dollars. For several randomly selected people from each category are shown in the table at the left. Assume that the population are normally distributed, the samples are independent, the population variances are equal. So all conditions of the test are met, guys. At alpha equal 10%, can you reject the claim that the mean earnings are the same for all 3 categories? Okay, look, guys. HO, you write mu1 equals mu2 equals mu3, it's a claim. You agree that this is the claim here. And HA, as I told you, it's the same language, don't change it. At least one mean is different from the others. And then we run the test. It is an F test. I'll talk about the F distribution tomorrow, but let me just do the test for now. And it's a last test, so scroll up, guys, it's ANOVA, analysis of variance. Any guesses, guys, what I should enter in here to run the test without looking? What do you think?
L1, L2, L3.
Exactly, but put a comma in between. That's it. It's as simple as that. Very easy test, guys. That's why I want to do it the first one in this section. All right. And all you need, the first 2 values, F and P. F is the test statistic. So F is right here. Okay. Did we make a mistake? I got a 0.7. What did you guys get? Did you get the same? Did you get what I have, or you got what you see in the table? I must have made a mistake somewhere.
I got something different. I got 2.889 for the, yeah.
Did I do anything that's not right?
I think you're L1.
Oh, a 60 I should have put. Okay. Yeah, in L2. L1. Oh. I put my data in L2, L3. I'm not sure anymore what I did. So anyway, I'm gonna go with what it says here. You should get this prompt. I think I used the wrong list, guys. I was putting data in a different list. So you will get F equals 2.889, which is the test statistic. You will get the p-value, which is 0.0685. And we want to compare with 10, guys. This is less than 10%. And if it is less than 10%, what's your decision? Is to reject HO? You can ignore the rest, guys. You don't need to look at the rest at all. Just the p-value, the F, and the reject the null, the p-value. We reject HO. Okay, what is the conclusion? If we reject the HO, guys, it's the same thing as the yellow sheet I've been showing you before, the conclusion. You reject HO and the claim happened to be in HO. You say there is enough evidence at the 10% level of significance to reject the claim that the means are all equal. And let's see the interpretation. There is enough evidence at the 10% level of significance to reject the claim that the mean earnings are the same. This is what we call ANOVA analysis of variance. Tomorrow, I'm gonna start with this exercise, guys. So I will send you this sheet, which is page 563 in your textbook. We will do this exercise. I'm gonna make sure that L1, L2, L3, and L4 are ready with the data sets. We will do it. We'll do also another example, probably 2 examples on the ANOVA test, and then we'll go back to section 10.1 and 10.2. That should be it for today.